previous video, linked in the description, we discussed the rotordynamic analysis of rotating equipment. In this video, we focus on our blade vibration analysis and strain gauge positioning capabilities. The components of a gas turbine are subject to high centripetal loads, vibrations and temperatures. Modern blades are constantly being pushed to their limits to achieve better performance, so it is important to accurately predict material stresses and expected component life. During testing, blades are fitted with strain gauges at critical locations in order to measure their stress condition. If measured stresses exceed a specific value, the test is shut down. Positioning of strain gauges can be complex. The number of gauges should be minimized to help with instrumentation lead-out and to ensure the test is representative of the final product. However, it is crucial that all potential failure modes are captured with sufficient sensitivity. Here at Fluid Engineering, we have developed our own in-house application to optimize the process of positioning strain gauges on blade faces for use in the safety systems on rotating machinery. In this video, we will present a breakdown of the process, beginning with a fatigue analysis. Finite element analysis models are used during design to identify and resolve any issues early on. These models must consider both the radial forces due to rotational speed and any vibrational modes which may be excited during operation. First, a static analysis is conducted at the maximum operating speed to predict the deformed shape and induced stresses. Next, modal analyses are conducted, one for the undeformed or zero speed shape and one for the deformed maximum operating speed case. The changes in blade geometry and temperature under load affect the natural frequencies and must be captured in order to create representative Campbell diagrams and identify any problematic operating speeds. For a more detailed look at our blade analysis capability, please see our video on cyclosymmetric blade analysis. And for information on Campbell diagrams, see our video on Rotordynamics, both linked in the description. On screen you can see mode shapes and stress distributions for the first 6 modes of the blade. Once the modal analysis has been generated, cyclic stresses can be scaled so that the maximum life-limiting stress combination within the blade can be found. Once a strain gauge position is identified, the measured stresses can be calibrated to predict the maximum stress in the blade and appropriate limits set within the operating control system. This is performed for each mode. In this case, the SN curve for a standard aerospace grade titanium alloy was used to produce a limiting stress envelope for a specified lifing requirement. The effect of elevated temperature on material strength, the presence of local stress concentrations, and the level of safety factor to apply must also be considered, as they affect the acceptable stress values and can vary across the blade profile. Here you can see how the static and dynamic stresses at each nodal location are compared against material fatigue strength data to identify the likely failure point for each vibrational mode shape. The next step is producing a Campbell diagram like the one shown on screen. The red line indicates the running speed, and the green lines indicate the modal frequencies at different rotational speeds. The black line indicates natural frequency of the rotor through different speeds. The disc itself also exhibits modal behavior, referred to as disc nodal diameters. These are represented visually by the animations on screen, and are accounted for by plotting engine order or EO lines on the Campbell diagram. Any intersect near the running speed is a potential cause for concern and should be investigated further. Now we know the relevant modes and the life-limiting stress proportions across the blades. However, strain gauge size, positional and angular deviation when fitting, the distance of the gauges from areas of high curvature, large stress gradients and principal stress directions must also be considered. Our in-house application considers these requirements within the search algorithm, which investigates node by node to find the appropriate positions. The efficiency of the program is increased through the use of map traversal methods. The output of this tool is a list of candidate strain gauge positions for specific modes or combinations of modes. A contour plot is then generated by overlapping modal results to indicate areas that capture multiple modes. Visualization tools like this and high quality data produced from our simulations enable our engineers to optimize solutions for our customers, resulting in reduced costs, improved test data, and ultimately better component performance. Here at Fluid Engineering, we pride ourselves on our agility and ability to tailor solutions to each customer's unique requirements. We offer this capability as part of our full turnkey design and analysis package, or as a standalone service that can be customized for your individual needs. If this is something you are interested in, please visit our website, reach out to us on LinkedIn, or give us a call to arrange a visit to our Dorking-based office. Thanks for watching.